8.5 and 8.6, we're going to talk about probability. In 8.5, we're going to start by talking about the fundamental counting principles. This kind of tells us how many ways something is possible. So if an event can occur in m different ways and then another event can occur in m different ways, we would multiply those two amounts of different ways together to find our total amount of possibilities that we have. With this section, it's super important to pay attention to the wording. You'll see in some examples that we do where the order matters, sometimes the order doesn't matter, and then we do different math depending on kind of what the question's asking. So pay attention to the wording of the questions. Most of these questions are going to be word problems. Just make sure you read it carefully. We're also going to kind of talk about things that are common knowledge. So anything that we do in the notes and anything we do in the homework that is kind of common knowledge, you need to remember when it comes time for the test and quiz. So there is a PDF of a deck of cards on Canvas that you're going to need to know to do some of these questions. How many cards are in a standard deck of cards?
52.
52. How many of those 52 are red? Half of them. So 26. How many cards have a heart on it? 13, a quarter of them. Perfect. So the deck of cards is there to help you for now. Use it to help you with the card questions on the homework, but we are going to expect you to know that come time for the test or quiz. So another thing that is common knowledge, let's look at example 3. It says how many different pairs of letters from the English alphabet are possible? Well, how many letters total do we have in the English alphabet? 26 letters. So it's asking us how many different pairs of letters can we have? How many are in a pair? 2. So if we wanted to, we could say our first pair is A and A, then we have A, B, A, C, A, D, but this would take us all day. Because once we get through all the A's, then we would have to say all the B's, all the C's. Yep. So we have a mathematical way that we can come up with the amount of possible pairs that we have. So how many different options could I have in this first letter? I'm in the first letter for my pair. 26, because it could be 26 letters. How many could we have in the second pair?
26.
We could also have 26. So we multiply these together to find out the total amount of pairs. So 26 times 26 would be 676. Now we have to be careful with the wording. If this question said with no repeating, so it said the same thing, but the letters cannot repeat.
That's weird.
How many possible letters could I have in the first one? 26. But let's say that B was my first letter here in my pair. We can't do B again. So how many possible options can we have in the second letter? 25. Awesome. So we would multiply 26 times 25 if it said without repeating. Awesome. 650. Telephone numbers in the United States currently have 10 digits. The first 3 are the area code and the next 7 are the local telephone number. How many different telephone numbers are possible within each area code? Note that at this time, the local telephone number cannot begin with a 0 or 1. So let's start with the beginning. It says that our phone number has 10 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The first 3 are the area code. So the first 3 is going to be 954. Can't change all of the numbers that we're looking for. All of our possible options are going to have the same area code. So we're really just looking at the next 7 spaces. How many digits total do we have?
10.
So digits are numbers 0 through 9. So Santi, how many digits total do we have?
9,
No, 0 through 9?
10.
10.
That's
Yeah, good job. So we've got 10 possible digits total, but the first number cannot begin with 0 or 1. So our first number could be 2, 3, 4, 5, 6, 7, 8, 9. So how many possibilities do we have for this first number?
8.
8. Perfect. Now it doesn't tell us anything about the second number, and we could repeat here. So how many possibilities do we have for the second number?
8.
10. We have 10. Could be anything 0 through 9. So we've got 10 possibilities here. What about the third number? 10. Fourth, 10. Fifth, 10. Sixth, 10. Seventh, 10. What do we do with all these numbers? Multiply them all together. So we have 8 with 6 zeros. 8 million possibilities here. So you'd be sitting here until next year trying to count all the possibilities if you were to write them all out. You'd be in college by the time you come up with your 8 million. Another common question that we might see is one that deals with ATM pins. So let's say we had a 4-digit ATM pin. So we have 4 numbers here. And let's say that the last number has to be even. But let's start with the first number. How many possible options do we have for our first number?
9. 10.
We have 10. We could put anything 0 through 9. So we've got 10 possible options. What about the second one?
10.
10. What about the third one? 10. If our last number has to be an even number, how many even numbers do we have?
4.
4. 2, 4, 6, and 8. So we've got 4 possibilities here. So multiply all of these together. This would give us 4,000 possible ATM pins. All right, next, we're going to talk about permutations and combinations. So we're going to see this symbol for permutations. It's going to have a big P. We'll have NPR. Combinations are going to have NCR. The difference between a permutation and a combination is in permutation, the order matters. In a combination, the order does not matter. And then one important thing to note here, N is always bigger than R. So N is always going to come first. Think about it. N comes first in the alphabet. N is always going to be bigger. Bigger number comes first. So looking at this box here, the definition of a permutation, it says a permutation of n different elements is an ordering of the elements such that one element is first, one is second, and one is third, and so on. If something is first, it can't also be second. So the order matters here. So looking at example 5, it specifically says how many permutations of the following letters are possible. So it tells us permutation. That means that the order of each letter matters. So how many letters total do I have? 6. How many letters from A, B, C, D, E, and F could I put in the first spot? 6. But let's say A we put in the first spot. So that means I can't put A in the second spot because it's already in the first spot. How many possible letters do I have for the second spot now? 5. Let's say I put F in the second spot. So I have A in the first spot and F in the second spot. How many possibilities do I have for the third spot? 4. And so on. Times 3, times 2, times 1. This looks super similar to something we did in 8.1. What do we do or how would we write it if we multiply? Awesome. Factorial is what it's called. But 6 exclamation point. This is 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. Anybody know what 6 factorial is? 720. Awesome. So it says the number of permutations of n elements is given by n factorial. In other words, there are n factorial different ways that n elements can be ordered. Now looking at example 6, we have 8 horses running in a race. And how many different ways can these horses come in first, second, and third? So we care about 3 places, first, second, and third. How many possible horses could end up in first place?
1.
Well,
What? Wait, okay. 8 of the horses.
8 of the horses could end up in first place. So we could have 8 different horses be in first. But let's say our blue horse ends up in first place. Blue horse can't also end up in second place. So how many horses could end up in second place now? 7. What about third place? 6. Awesome. So here we have 8 times 7 times 6. So it's not always going to be 8 factorial to help us find our possible answers, because here we only care about 3 places. So we just have 8 times 7 times 6, which would be 336. So this is permutations of n elements taken r at a time. We had 8 horses, but we only cared about 3 of them, the position of 3 of them. So we could write this as 8p3. Some of the questions on your web assignment are just going to be written like this, where it'll say 8p3. If you see a question like this, we use this formula here. So this would be 8 factorial over 8 minus 3 factorial. So here we have 8 factorial over 5 factorial. 8 factorial is 8 times 7 times 6 times 5. I could stop here because I see that I have a 5 factorial on the bottom. And we know that these are going to cancel. So I'm just left with 8 times 7 times 6, which is exactly what we did in the last question. So this is like the algebraic way that we could find our answer. If we had 8 horses total, that was how many elements we had. We're only picking 3 of them. When the order matters, we would use this. So you could use it either way. If you like to write out the spaces and think about how many horses could be in first place, how many could be in second, they'll give you the same answer. Next thing we're going to talk about is distinguishable permutations. Distinguishable permutations, we divide out the repeats. And I'll show you what I mean by that when we do our first example. So example 7 says, in how many distinguishable ways can the letters banana be written? So for distinguishable permutations, we're going to take the total factorial divided by the repeated factorial. How many total letters do we have in banana?
Banana 6.
6. So 6 factorial up top, because that's our total amount. Now we want to see what repeats and how many of them do we have. Do we have any B's repeating? No. Do we have any A's repeating? And how many A's do we have? 3. So we're going to put a 3 factorial on the bottom. What about N's? We have 2 N's. We also need to put a 2 factorial on the bottom. So with this one, let's write it out. We have 6 times 5 times 4 times 3. I see that I have a 3 factorial on the bottom, so I could stop there. So I know that the 3 factorials are going to cancel, but I also have that 2 factorial. So let's write out 2 times 1, but do I need to put the 1 there? No. So our 3 factorials will cancel. You can multiply 6 times 5 times 4 and then divide it by 2, but I'm going to do a little bit more simplifying. 2 goes into 6 how many times? 3. So now I just have 3 times 5 times 4. What's 3 times 5 times 4? 60. So our amount of distinguishable ways is 60. So if it says distinguishable permutations, you do the total factorial divided by the repeated factorial. Next, we're going to look at combinations. So combinations, we said the order doesn't matter. So if I was picking 12 people out of this class to end up on a jury, does it matter the order of people that I pick? Does it matter if Santi gets picked first and then Michael gets picked second? No, because they'd all end up on the jury. If I was picking 6 oranges in my basket, does it matter the order that I pick them in? No, because they're all going to end up in the basket. So for combinations, the order does not matter. So for our combination, we have NCR, where N is the total amount of elements, and we're only choosing R of them. So if I had 32 people in this class and I picked 12 to be on the jury, we would say 32, choose 12, like this. And our formula would be N factorial over N minus R factorial times R factorial.
What is R?
The second number. The amount of people that are getting picked, you could say. So example 8a. It says, in how many different ways can 3 letters be chosen from the letters A, B, C, D, and E? The order of the 3 letters is not important. So it says that the order is not important, so I know that this is going to be a combination. How many letters total do I have?
4, 5.
We have 5 letters total. And how many are we picking? 3. It says, in how many different ways can 3 letters be chosen? So 5, and we're choosing 3. So we have 5 factorial over 5 minus 3 factorial times 3 factorial. So let's write this out. Up top, we have 5 times 4 times 3. I could stop here because I see that I have a 3 factorial on the bottom. I'm just going to write it all out to show you. 5 times 4 times 3 times 2. Do I need to put the 1? No. 5 minus 3 factorial would just be 2 factorial. So I have 2 times 1. Do I need to put the 1? No. And then times 3 factorial, so that would be 3 times 2. So up top, we have a 3 and a 2 that cancel with the 3 and the 2 on the bottom. We could also simplify 2 goes into 4 how many times? 2. So what do we have left? 5 times 2, which would be 10. So there's 10 different ways that 3 letters can be chosen from the letters A, B, C, and D, and E. Let's look at B. So a standard poker hand consists of 5 cards dealt from a deck of 52. How many different poker hands are possible? After the cards are dealt, the player may reorder them, so the order is not important. So order is not important, so we know that it's going to be a combination. How many cards total do we have? 52. And how many are we choosing? 5. So when we put this into our formula, we have 52 factorial over 52 minus 5 factorial times 5 factorial. 52 minus 5 is 47 factorial. So up top, we've got 52 times 51 times 50 times 49 times 48 times 47. I would recommend not continuing to write all the letters or all the numbers out here. Once you see that it's going to cancel at the bottom, especially if you have big numbers like this, just stop. It's going to cancel out with the 47 factorial on the bottom. But I'll write out the 5 factorial. 5 times 4 times 3 times 2. So 47 factorials are going to cancel. If you wanted to from here, you could multiply 52 times 51 times 50 times 49 times 48 up top, and then divide that by 5 times 4 times 3 times 2. I'm going to just simplify some more, so it's less work that we have to do to multiply. 5 goes into 50 how many times? 10 times. 4 goes into 48 how many times? 12 times. 3 goes into, we could say 12, how many times? 4 times. And 2 goes into 52, how many times? 26. So what I have left is 26 times 51 times 10 times 49 times 4. So if you cancel out like this, be super careful with the math. We've got 26 times 51 times 10 times 49 times 4. When we multiply all of these together, we get 2,598,960.